Today we are gonna have the 13th session of our cognitive neuroscience course with pragmatic and clinical applications, or pragmatic and clinical approach. And what I'm gonna do today, I will cover the last chapter of the textbook that we have in this course, which is the Fundamentals of Cognitive Neuroscience course that we highly recommended everyone to have, by Dr. Gage and Dr. Bars. And as I told you, we invited Dr. Gage and Dr. Bars to attend another session that we have, to have this opportunity to learn from their side as well. So today we are going to cover the idea of brain development and brain and cognition development. And if you want to read the material, you can find the material in the 14th chapter of this textbook. And I will obviously cover some other topics and some personal experiences regarding the brain development and importance of brain development, and some technical issues about that as well. But as we cover the last chapter of this, or this last title of this course, the next session, session 14, I will try to give you some ideas and some personal experiences in terms of how cognitive neuroscience could help people to change their clinical practice, or how cognitive neuroscience could reshape the future of different areas like education, psychiatry, clinical psychology, different pragmatic applications, and how you might be able to be a sort of cognitive neuroscientist with skills to be able to be impactful in this area of science in the future. So that would be the main composition of session 14 that will be next week. And the week after, we will have another meeting discussing about the questions that you have. And we will have Dr. Bars. Dr. Bars has already confirmed that he will be joining us for not next session, the session after. And then the week after, we'll have the final exam. And we have designed the last few sessions in a way that if you attend the last few sessions and just do your homeworks and just do the final exam, you will be able to get certified. You need to be kind of highly active in the last couple of weeks. That would give you an opportunity to be able to wrap up whatever we have, and also it would give you this opportunity to get certified in this course. And obviously, if you want to get certified with honors, we provided an instruction in the channel space that we have, and if you want to see the details, you can find the technical details there. So if you are interested to have a specific question for the last session, which is basically the session 14, that you like me to cover, or a specific area that you are interested to discuss, to be discussed, just send me a message, and I will try to cover those questions and ideas for the last session as well. So that will be the plan that we will have for the next session. What I'm going to cover today, I will discuss about how we do cognitive neuroscience studies with brain and cognition development. I will talk about brain before birth, and I will discuss about the brain development after birth, and then we will discuss about language development, social cognition development, and I will end up discussing about how different injuries in early childhood could change the brain and the brain processing, and how these injuries could be repaired over the time. So we'll discuss about those things, and then obviously how brain would get into the path of development, and how we might be able to learn from this development pathway to help kids to have a better developmental milestone and having a kind of a more healthy development pathway. Okay, for the first part, first we will discuss about some of the methods that we use in cognitive neuroscience to study brain and cognition development, and I will start from this point discussing about different study methods that we have. But before getting to this question regarding the methodology and the technologies that we are using for brain and cognition development, let me start with asking a question, okay? So I'm going to ask you a question regarding your own childhood and brain development. Let's start to think about the first memory that you can remember from your life. So please start to think about the first memory that you can bring in your mind from your own childhood. I'm not sure if you can remember something from the age of 3, 4, 5. What is the first memory that you have in your mind from your childhood? Try to remember or retrieve that memory, and I'm going to ask you a few questions regarding that memory. Panyan, have you developed the survey? Could we share the survey in the chat space?
Yes, sure. I'm just sharing there is a short Google form like what we had last session, and I shared it in the chat space. So please click on the link and answer the questions regarding the first memory that you remember from your life.
Okay, yeah. So this is this is not going to be a study. It's just we are just collecting the data just to discuss it in this class, as we did for the survey last week. We shared the data that we collected last week as something like an open database inside the group. So if somebody is interested to take a look inside and do some further analysis, please feel free to do that. And it would be nice if you even share the findings that you have inside the group. But it is not supposed to be used for any sort of publication. So we do not have any, let's say, ethical approval for that specific survey. It's just something like educational things that we do inside the class. So please go ahead and fill in the survey, and then we'll discuss about the specific implications of these discussions and these questions. As you can see here, the first question is about the type of feeling that you have about the memory. Is it something like a bad feeling or even type of memory, or positive or neutral? And then what do you feel when you retrieve that memory? Obviously 5 would be neutral, and 0 would be extremely bad, 10 would be extremely good. And then the age that you had that specific memory, and whether you see that memory, when you retrieve the memory, do you have the memory from your own eyes, or you feel that you see it from something like a third person view? You see yourself from outside and doing that specific type of memory that you have in your mind. And then just ask another question regarding how many memories you have in your mind regarding your early childhood before your 5th birthday. And basically, it was not supposed to be nothing to in full details.
It's just sorry, I haven't checked it. It's not my fault. So I just put it as another visual analog scale. But please write from 0 to 10. How many memories do you remember? Not about how vividly you are remembering the memory. Sorry for this technical problem. It was supposed to be a short question that you enter the number, but
okay, yeah. that's totally fine.
If it is mixed between first and third person view, you can just say third, because that is more towards the third when you have a combination of both. We will get back to this question at the end of the class. So I have a specific part at the end of the class. I'm going to discuss about this issue regarding early childhood memories and how that is related to the discussion that we are going to have today about brain and cognition development. Okay, good. So now you have a brain activation that engage you to the class and discussion that we're going to have. I hope that we will discuss about the specific implications, and hopefully Panyan would be able to do some, Panyan and Mohsen would be able to do some analysis on the data as well, and show us the results as well, and we'll see the results together at the end of the class today. Okay, so what are the technologies that we use for studying early childhood development? Obviously, one of the technologies that we can use is EEG-ERP, which is an electricity-based method. We know that EEG would have a really good temporal resolution, and There are challenges in terms of movement, but it is still doable. It is not that much expensive, so it depends on the EEG devices. We have EEG devices up to something like $1,000, up to a couple of, let's say, up to $70,000-$80,000. But that is usually the usual range of EEG ERP devices, and we can have the different versions. But it is pretty much inexpensive, and it is considered as noiseless. And by noiseless, we mean that it doesn't have too much loud, sound noises. So it doesn't disrupt or disturb very much kids. So that is the advantage, that we can use it easily for kids. But the other technology that we use in this field, which is still an electricity-based method, or I should say magnetic-based method, it's called magnetoencephalography, which records magnetic field changes. The device is a couple of $1 million. So we make devices from something like $1 million up to 7, 4, 5. It depends on the type of the technology that you want to use, and they have a pretty much high maintenance rate as well, because they need helium, and there are challenges. And even the cage that we put these devices inside, because they need a specific, let's say, room that you can put the device inside that room. And sometimes even having a large room that would give you enough space to put the device inside would cost you up to something like $1 million. So it is not a really easy technology to use, but the good thing is it is still noiseless. It has good both temporal and also spatial resolution together, and especially for studying kids, it's an interesting device to be used. So you can even have kids with his mom or her mom sitting and having the kid on her lap, just doing the study. So there are lots of potentials for using MEG for childhood development. The other technology that we use, and we discussed about that before, would be fMRI. And you can imagine that having kids inside fMRI is not something easy to do. And almost all the studies that we have in early childhood, we just put people in a sleep, and then we put the sleeping child inside the scanner. And meanwhile, you can easily understand that those who have used fMRI, they know that the device is really noisy. So we need to use noise reduction, ear pod, or different sort of technologies. And it's not very much easy to do, and it is really sensitive to movement. And because it is really sensitive to movement, it is really hard to have really good fMRI signal from small kids. But people are still doing different studies with fMRI among early people in the early childhood. So it is still doable. The other technology is what we call functional near-infrared spectroscopy. And functional near-infrared spectroscopy is using a version of red light, or sometimes a type of laser, to just penetrate inside the skull and just record the changes by sending the light inside the skull and just recording the changes in the level of oxygen and changes in the level of blood that we have in vessels over the brain. So there are specific potentials with these technologies, but this one is less expensive than the fMRI devices, so they could be something like $20,000 up to, if they are laser devices, they could get up to something like $100,000 as well. Depends on the number of channels that you have for them, and whether they are based on light or they are based on laser. So there is a distinction between these two devices, and there are pros and cons for this specific device. But it's important to know that both fMRI and near-infrared spectroscopy, both of them are based on the level of oxygen. Most of the time based on level of oxygen that we have inside the brain, as something like a proxy measure for neural activations. The other methodology that we usually use is a structure-based imaging method. So using structural MRI for seeing how the brain is being under the process of development. As you can see here, there are some analytic steps that we usually take. We usually take the MRI in the what we call native space or subject space, and then we register the subject space to what we call the standard space, because being able to compare the structures with the standard atlas. And we discuss about the standard atlas and how standard atlas are going to be used. So we put all the different types of or sizes of the brain to one single atlas to make them standardized. So that is what we call making a standard brain, to have the same sizes. And then when we have them inside the same sizes, we can say, okay, this specific location is always dorsolateral prefrontal cortex, or this specific location is always amygdala, independent to the size of the head or brain that you have, whether it's something like a really big head like my head or a smaller head. So independent of the size, you can see that we can use them in what we call registered MRI space. And then we can do tissue classifications. We can just differentiate gray matter from white matter from subcortical, so we can differentiate those types of tissues from each other. And this is the way that we can do, at the end of the day, what we call corticometry. And by corticometry, and by corticometry, what we mean is we measure, if it's the sulcus or it's the specific gyri, we can measure the thickness of what we call gray matter. So we can say that it is something like, let's say, 3 meters is the thickness of gray matter. So we can measure the thickness of gray matter in different parts of the specific, let's say, gyrus, and we call that corticometry, or measuring cortical thickness that we have. And cortical thickness is a good measure of brain development. I will discuss about that, why cortical thickness is important in the process of brain development. I will discuss about those things. And then we can assign a color for each specific cortical thickness value. And for example, these areas, they have kind of higher cortical thickness, these areas have lower cortical. So depending on the measure of the cortical thickness, we can assign a color, and then we can have a cortical thickness map. And besides cortical thickness measure, most of the cortical thickness measurements would also include what we call measurement of the sulci and the gyri that we have, a measure that is related to what we call gyrification. And gyrification is related to number of gyri and sulci that we have. And in the process of development, I will discuss about that, we have changes in cortical thickness, and we have changes in the level of gyrification, or the amount of convolution and complexities that we have over the cortex, in a way that make the cortex having a higher level of cortical surface in a smaller amount of space that we have inside the skull. So that is the way that we measure the level of brain development. I will discuss about how these specific measures would be critical in terms of understanding the child brain development. So we'll discuss about those technical details in the next step. Okay, that was the first part of the class today.